Hi, I am Maria-Craciun and I will talk about a new way of expressing the Indian buffet process in probabilistic programming. This is a joint work with Hugo, Paquet and some Staton. So the Indian buffet process defines the distribution over infinitely wide binary matrices, and it can be used as a prior for infinite latent feature models. Our aim was to express the Indian buffet process without using truncation, so that is by keeping the model intact and without using hidden state. We will first review two representations of the Indian buffet process, and these are the sequential procedure and a stick breaking constructions. The first one needs hidden state in order to be implemented, and for the second one, we would get a program which does not terminate, so we would need some sort of truncation. Then we will take a look at our approach, which is inspired by slice sampling, and it also requires nested inference. So for latent feature models, we have a set of features, and we would like to automatically assign to each object a subset of those features in such a way that objects that share multiple features are very likely to be similar. However, in some cases, we might not know the number of features beforehand, or we want the number of features to grow with the size of the data. Then we would like to consider an infinite set of features. However, this makes the model non-parametric because we will have an infinite number of parameters. So we can record the assignments in a binary matrix, as we can see on the right. So here the program automatically found some good features. So the rows correspond to the objects and the features are the columns. Now, we can use the Indian buffet process as a prior for this type of matrices, which have infinitely many columns. We can describe the process using the following metaphor. So we have a restaurant which serves an infinite number of dishes, and each customer comes in one at a time and chooses some of the dishes according to the following two rules. The customer comes in and looked at the dishes that were chosen by previous customers and then picks some of them according to the popularity. Then the customer looks also at the other dishes and also picks some of the ones that were not touched by other customers. We can describe the Indian buffet process with strength parameter alpha using a sequential procedure. So the number of dishes that the first customer takes is distributed according to a Poisson distribution, and here, as a reminder, we have the PMF of the Poisson distribution. Then the ith customer comes in and he chooses dish k with probability mk over I, and here mk is the number of times that that dish k was chosen before. Then the customer looks at the other dishes and also picks some of them. So let's look at a little example. We have the dishes here. Then the first customer comes in and let's say he takes the first three dishes. Then the second customer comes in and he will independently choose from dishes 1, 2, and 3 with probability 1 over 2. So let's say he picks dishes 1 and 3, and then he also chooses, let's say, 2 more dishes. Then the third customer does the same thing. However, we can notice here that the probability of choosing dish 1 and 3 is going to be 2 over 3, and it's going to be higher than the probability of choosing the other dishes, which is 1 over 3. So he also chooses one more dish. Notice that if we want to implement this version of the IBP, we will need a hidden state in order to remember information about previous customers. So again, we record this in a binary matrix where the customers correspond to the row. So these are the objects, and the dishes correspond to the columns, which are the dishes. So notice that even though we have an unbounded number of dishes, each customer takes only a finitely many dishes at a time. So yeah, this is why we can use the Indian buffet process to define a distribution for this type of matrices. Now, another representation of the IBP uses the stick breaking construction, in which we first sample the dish probabilities mu k. Here, mu k is going to be the probability of dish k being picked by a customer. So we can sample this from a beta process. Now, once we have these probabilities, then a customer comes in the restaurant and looks at the dishes in order, and he picks the dishes according to their probability. We can see here, if we denote with that the row binary vector corresponding to the choices made by the customer, the distribution of a customer. Even though this representation is very neat and the customers only take finitely many dishes, if you want to implement this directly, then we would get a program which does not terminate. Okay. So we have seen two existing representations of the IBP. The first one introduces a hidden state, and the second one gives a program which does not terminate, so it needs truncation, some kind of truncation. And by truncation, I mean that, for example, we can use only finitely many dishes. However, this will not preserve the desired distribution. So our approach is inspired by slice sampling and introduces an extra variable S in such a way that if you have this joint distribution of the customer and S, and we sample from it, and then we discard the S values, we will be left with values for the customers which are correctly distributed. In the literature, this variable is called the slice variable, and we can also decompose this distribution into two. One is for the slice, given the dish probability is mu, and the other is for the customers, given the slice and dish probabilities. So what we can do, we can first sample a value for the slice, hopefully using finitely many dishes, and then use that in order to sample a value for the customer. In our approach, we define the distribution of the slice in such a way that once we have a value for it, then the conditional density of the customer will be greater than 0 only for finitely many customers. So it's going to be easy to sample from, and it's going to actually be a uniform distribution on a finite set. So if you want to implement this, we can do, for example, sample lazily the dish probability is mu, and then sample a value for the slice and use that to get a value for the customer. But if we have multiple customers, of course, we need different values for the slice. So let's take a look at the distribution of the slice. We don't need to worry about the details, but we have the infinite product, which we cannot compute. However, we can compute for any S a value for the normalized density of the slice. So we can use an MCMC method in order to get samples for it. This can be done, for example, by using this program. So we can sample the slice from a uniform distribution, then we weight the program by the normalized density, and then return the slice. If you want to, for example, condition the customers on some data D, then we will need to perform inference also to get the slice values, but we will also need to perform inference on the bigger model. This, however, leads to nested inference, for which expressivity and asymptotic correctness is challenging. So as I said, our work is inspired by slice sampling, and it also appeared in the context of Bayesian non-parametrics, was also out of it. So to recap, we have seen two representations of the Indian buffet process and how we can use it as a prior in infinite latent feature models. And we have shown that we can express the Indian buffet process using nested inference, but without using truncation or hidden state. We also performed some basic experiments with this approach in lazy PPL, which is a Haskell library for probabilistic programming, and it makes use of infinite lists via laziness. So we mentioned nested inference, which is challenging, so we would like to pursue that in the future, and we would also like to consider extensions of our approach to generalizations of the IBP, such as the two-parameter IBP and Gibbs type IBP. It would also be interesting to connect formal questions about expressivity with formal computability arguments. This was all. Thank you for your attention.